So let's say that we start. Welcome everybody.
Ora si registrerà la conferenza.
And I am glad that you decided to attend this second webinar of the series in Geobiology. It is co-organized by Italian Geological Society and by the Department of Earth Science at University of Naples, the Department of Biology, and also University of Bologna. And I'm very happy to introduce the speaker of today. Today we have Ariel Amber, Arizona State University. Ariel is a scientist and educator interested in Earth, past and future as an inhabited world, and the prospects for life beyond. His group develops novel geochemical methods to study topics ranging from the chemical evolution of the atmosphere and ocean to human disease. Ariel has been trained as a geologist and chemist. He got a Bachelor of Science from Harvard in geology and chemistry. Then he moved to Caltech, where he got a Master of Science and PhD in geochemistry. Before joining the Arizona State University, he was a faculty member at the University of Rochester. Now at the Arizona State University, Ariel is a president professor and in the Faculty of School of Earth and Space Exploration and in the School of Molecular Sciences. And he is also a distinguished sustainability scholar in the Arizona State University Global Institute of Sustainability. Ariel Amber directed the Arizona State University Astrobiology program from 2009 to 2015, and is the director also of the Center for Education Through Exploration. And I don't know if you are aware of the magnificent things that this center is doing. If not, please have a look at their page, at their courses, online web resources, and their virtual field trip that are really fantastic. Ariel is also a fellow of the American Geophysical Union, the Geological Society of America, and of the Geochemical Society, and of the European Association of Geochemistry. He received several awards, including the Howard Hughes Medical Institute professor. He's also an Howard Hughes Medical Institute professor, and he's a recipient of the Donald Nonat Medal and the Arthur L. Day Medal of the Geological Society of America. And we are really happy to have Ariel here, that he will talk on life on other planets. And well, it's enough. Please, Ariel, share your screen.
Well, yeah, thank you for the generous introduction. I put some links in the chat to the education website that you mentioned, or the website of the Education Center. Okay, let's hope this works now.
Yeah.
Do you see my screen?
Yeah, perfectly.
Great. So yeah, so so thank you for the invitation. It's really an honor, and I look forward to visiting Mariano and others in Italy at some point when international travel is a little less crazy, which it's starting to become, which is good. So what I'm going to do here is give a presentation about looking for life on other worlds, but through the lens of biogeochemistry. And I'm going to focus very much on what I, as an Earth historian and somebody who studies the history of the intersection of life and environment on Earth, think that we geoscientists have to say about this search for life elsewhere. And this is I say it's a perspective. It's a particularly personal perspective. It's through the lens of my research and the research of my collaborators and colleagues. There are many different ways that one could approach this. This is a particular look from a particular perspective, but I hope there are some generalities that everybody will resonate with. So first of all, the challenge of looking for life on other worlds is very nicely embodied by this image here. This is a family portrait of us. We're all in this picture, every one of us. You didn't know you were being photographed when this was happening, but you were. So this is a picture taken from Saturn, from the Cassini spacecraft orbiting Saturn a number of years ago, of the Earth. That little dot there, that pale blue dot, is us. We were there that day. And the challenge of searching for life on other worlds, in particular searching for life on planets orbiting other stars, which is my main focus here, is the challenge of detecting, of telling from a single pixel or a few pixels of information whether or not there's a biosphere on a planet that is tens or even hundreds of light years away. So this is a huge challenge, as you might imagine. And as it turns out, geoscience and the study of Earth history had a lot to say about how we might want to navigate that challenge, how we might want to approach it. And that's what I'm going to talk about here. But before we get to that, I want to talk a little bit about, why we're even engaged in this search and how we should approach that search. And I think this quote by Carl Sagan, who those of you who are my age or older know who Carl Sagan was. I've learned that a lot of the younger folks, Carl Sagan, who is that? So Carl Sagan was a science popularizer, but also an astronomer and planetary scientist who was really a pioneer in thinking about space exploration and the search for life elsewhere. And he had this wonderful quote. It's actually from a novel he wrote called Contact, I think. The universe is a pretty big place. If it's just us, it seems like an awful waste of space, which is a nice and hopeful kind of philosophical statement, and a probabilistic one, right? There's some logic to it, right? There are so many trillions of stars, and we now know that so many of them have planets, that it's perfectly reasonable to hypothesize that if Earth is a typical place in the universe, which we think in physics and chemistry it is, if Earth is also typical biologically, then since there are many planets out there and many of them probably have conditions that are kind of like Earth, there should be life all over the place, right? And so we should be able to look for it and find it. And this is again, it's a logical argument. It's somewhat philosophical because the reality is we don't know. But this is, I think, what motivates many of those who are engaged in the search for life beyond Earth. That it seems like there ought to be life out there, so let's go find it. The challenge that poses to science, to the scientific exploration, is that there's a fine line between saying that, well, I think life is probably common out there, and turning this into a bit of a belief-driven quest, right? We very much at some level want to, many of us anyway, want to believe that we are not alone. And this gets philosophical and almost religious. It gets deep into the human psyche. No human being wants to be alone, and you translate that to the civilization. No civilization wants to be alone, and you translate that to the human species. The human species doesn't want to be alone. And we feel this very deeply. It's instinctive and intuitive across, I think, most human beings. So at some level, we want to believe that we aren't alone, that there's more out there. That really is the impetus for a lot of religious belief too. But in the modern era of Western science being very dominant in the culture, that sometimes gets translated into this desire to believe that there is life elsewhere, and that we are part of some, teeming galactic civilization of some sort or another. And you just have to glance at popular fiction, at popular culture, to see that it is saturated with the notion that we are not alone, that there are alien life forms out there, intelligent life forms out there, life forms that may be more intelligent than us. Some of them may be scary and nasty and dangerous. It's not necessarily a safe universe out there, but by and large, if you look at science fiction, for the most part, it leans in the direction of benevolence, of the notion that it's certainly better for us to explore and join and find and join hands in some way with alien intelligences that might or must be out there, depending on your point of view, than it is to worry about what might happen. And this has all the features really of almost a belief system, right? And this is very deep in the culture, and I think it's very deep in most of us who engage in this kind of science. I grew up as a Star Trek fan when I was a kid, and I can't pretend that childhood fascination with Mr. Spock and the USS Enterprise doesn't in some way emotionally resonate with my interest in research about there being life elsewhere. So these things are very deep. And that poses a challenge to the scientific investigation, because we need to avoid the danger of this turning into sort of a quest for a holy grail, right? That to turn the scientific enterprise of trying to understand life in the universe into a quest for life. And the problem with that is that when it turns into a quest, then there's an answer that's a good answer that we want, which is, oh, there's life out there and we found it. And then there's an answer that depresses us if it turns out to be true, which is that, oh, life is very rare, or maybe even we're alone. Because the fact is we don't know, right? We don't know. We're engaging in the search because we aren't sure. Carl Sagan's quote is very appealing and it seems logical, but it's just a hypothesis. And as we all know from the history of science, hypotheses, especially hypotheses that seem very obvious to everybody, often turn out to not be true, or to be falsified when we start to look at them more carefully. So we need to be careful not to turn this into a quest where there is a right answer and a wrong answer, because then the danger is that we will fool ourselves. So this is a warning to us, right? We need to be careful because we don't want to fool ourselves. And we know that we can fool ourselves. We just need to look at the recent history of science to see that. So if we go back 100 years, for example, and look at planetary astronomy, cutting edge planetary astronomy of 100 years ago, so the kind of the equivalent of what we're doing today, you know, astronomers, including famous Italian astronomers as well as American astronomers, looked at Mars and through the best telescopes of the day. And on the left here is what Mars really looks like. And on the right are the diagrams that these astronomers drew of the surface of Mars. It was their best interpretation of what they were seeing through the best telescopes of the era. And what they saw were these grand linear structures, which many interpreted as artificial because they seemed to be so linear and extensive. And so they interpreted these as canals built by a sophisticated civilization on a planet that was drying out because they could see there's no blue on Mars, so there's no oceans. So they imagined scenarios of a planet that was becoming uninhabitable and an intelligent civilization building canals to move water around. And so this took hold in the popular culture. And here from 1907 is a clip from the front page of the New York Times, right? Mars inhabited, says Professor Lowell. Lowell was a very famous astronomer in the United States around the turn of the 20th century. So what was going on here? Well, the astronomers were fooling themselves, right? They were looking at the limits of resolution of their instruments, trying to interpret what they were seeing, and their interpretation, what they were seeing, was biased by what they wanted to see in some level, right? And so what was an objective investigation of what's on the Martian surface turned into a very subjective interpretation of what must be there by well-meaning, objective, well-trained, smart scientists, and then that took hold in popular culture. So we need to guard against that, right? And that's what happens, unfortunately, when this becomes a sort of motivated quest. So Richard Feynman, famous physicist, late physicist, passed away a number of years ago in the US, had this great quote. He was a good popularizer of science. The first principle of science is that you must not fool yourself. And you need to realize that you are the easiest person to fool, right? So we need to become very objective about this search, as objective as we can be. And you don't need to go 100 years ago, right? You can just look a year ago. If you follow this science in popular culture and in the literature, there was a huge furor about a year ago about the possibility of there being life on Venus because of reports of phosphine in the atmosphere of Venus. And I don't want to go into that whole debate, but if you follow that debate, that came under a lot of very skeptical attack very quickly by a lot of the science community. And I would say that science was somewhat well-meaning, well-intentioned by good people, but somewhat motivated reasoning. They interpreted the data in a particular way that I think biogeochemists looking at that same data and the context of the Venus atmosphere would be pretty skeptical about even hinting that what's being seen is likely to be biological in origin. So this challenge of trying to be very objective and not letting our imaginations and our desires run away from ourselves, I think is very current. It's very current. So when we talk about astrobiology, about the search for life elsewhere, I like to think about it as not the search for life elsewhere. I like to think about it as it's the science of astrobiology. And what is the science of astrobiology? And I should cite here Bruce Jakowski, from who I sort of borrowed this. He's a planetary astronomer at University of Colorado. He likes to define astrobiology this way, which I like very much. Astrobiology is the study of the origin, evolution, distribution, and future of life in the universe. And I should add here, whatever it is. So if it turns out that life is common, we want to know that, and we want to understand why and how that is. But if it turns out that life is rare or unique to Earth, which to us right now seems unlikely, but we don't really know, if that turns out to be the case, we want to know that and we want to understand that as well. Either way is equally scientifically important. Either way is equally scientifically interesting. We could spend an hour talking about why I think actually the possibility that we are alone would be more scientifically challenging and hence important in many ways if it turned out that life is unique on this world. But we don't know, right? Whatever it is fascinating and important and interesting. What we want to do is not necessarily discover life to satisfy our emotional yearnings, although they're there, we need to acknowledge that they're there. as a science, we need to be disciplined and say, we want to know if there's life out there or not, and we want to know where it is and not, and we want to know why it is where it is and why it is not where it is not. That's turning this into a scientific investigation. Now, one of the problems, and this will bring us now to geology in a second, one of the big problems I think in this field is that it is very observational and not really guided by theory. We don't have a theory even of the Earth as an evolving biogeochemical system, right? I mean, our Earth science is still very much looking at the past to try to figure out what happened and then make up sort of stories about why it happened the way it did. But we don't really have a predictive theory. And the problem is, without a predictive theory of how the Earth evolved, it's very hard then to have any kind of generalizable theory of how Earths evolve, which then means it's very hard to predict whether a given planet might be a good place for life or not. We're in the very rudimentary stages of that. I mean, we have mantras like following the water. Well, we want to look for places that have water because we know that life as we know it needs water. Okay, great. That's fine, but let's understand we're limiting ourselves first of all to life as we know it. That's probably sensible. But life needs a lot more than just water. Water is actually very common in the universe, so that's not really much of a criteria. So, you know, what's needed is a much more sophisticated understanding of what leads to life on a planet, and how the fingerprints of life manifest on a planet, that allows us to generalize it to other worlds. And that's what I want to try to get across today in the next 30 minutes or so of this talk, how our study of Earth history can inform the development of such a theory. And this is just showing you here the evolution of Earth science, right? You go back to James Hutton, you know, one of the founding fathers of geoscience, right? He wrote a book called Theory of the Earth, Volume 1, and then flash ahead to the 1980s when Don Anderson, geophysicist at Caltech, wrote The New Theory of the Earth. But that work doesn't really incorporate biology in any serious way. What's really needed is something that is more integrative, that incorporates everything from the core to what's going on at the Earth's surface, and how that changes over time, and in a way that is generalizable, in a way that's really a theory that one could generalize to other objects that are not exactly like Earth, that we have confidence in understanding well enough to generalize to other Earths. So we need to really have a book that is a theory of Earths. It's probably not a book, it's a whole field of study. Okay, so let's get into the science. That was a lot of philosophy and framing, but I think it's really important to have that philosophy and framing before we dive into the science. So let's dive into the science. So what's motivating the science I'm going to talk to you about? What's motivating it is, in particular, that's what's coming soon, very soon, certainly for students who are listening to this in your careers, is the spectroscopic search for biosignatures. And this is basically looking at light passing through the atmospheres of planets orbiting other stars as those planets transit the disks of those other stars. The transit method, looking for dips in light from a star as planets transit across the face of those stars, is one of the main ways that we discover planets orbiting other stars and get some of their characteristics. One of the characteristics that we are just starting to figure out how to get is the atmospheric composition, by looking at the light passing through the thin atmosphere at the edge of the disks of those planets, and looking then within those atmospheres for biosignatures, for gases that are indicative of biology. Within that world of thinking about biosignatures, of signatures of biology within planetary atmospheres, what looms large is oxygen. So this here is an oxygen bubble being evolved from a cyanobacterial mat. So we know that life makes oxygen, certain types of life that is photosynthetic, of a type of photosynthesis that dominates the Earth and that leads us to have an atmosphere that's 21% oxygen on Earth. You know, we wouldn't have that atmosphere if not for photosynthetic biology. Oxygen looms large because we know that biology makes it. We know that to have a planet like Earth around a star like the sun with a 20% oxygen atmosphere requires biology to be producing it. But also we focus on oxygen because we can detect it from astronomical distances. And the nice way to illustrate that is by looking at Earth, Mars, and Venus. So what you're seeing here at the bottom is Mars, in the middle is Earth, at the top is Venus. And to the left there are infrared spectra, part of the infrared spectrum, showing you at the top. Let's go from the top, let's start at the top, look at Venus. So Venus has an atmosphere that's about 90 bars. It's almost 100 times the pressure of Earth's atmosphere. That's almost entirely carbon dioxide. So when you look at Venus atmosphere in this part of the infrared spectrum, you see this very large absorption feature due to carbon dioxide in the atmosphere, and you don't really see much else. We go to Mars. Mars is a very, very thin atmosphere. Instead of an atmosphere of 90 bars of pressure, it's an atmosphere of 6 millibars of pressure. It's you know, my laboratory uses mass spectrometers, and that's, you know, 6 millibars is almost a vacuum for a mass spectrometer, right? So it's a very thin atmosphere, but it's also mostly carbon dioxide. And so if you look at the Mars atmosphere, spectroscopically, it looks remarkably like Venus's. It's mostly carbon dioxide, and that's all you see. When you look at Earth's atmosphere, you still see a carbon dioxide feature, but carbon dioxide is a minor constituent of Earth's atmosphere. It's significant but minor, in part because biology is pulling it out of the atmosphere and into organic and also inorganic carbon. But you also see this feature here, right? You see this ozone absorption feature. So ozone is a molecule that absorbs very strongly in the infrared. So even though there's very little ozone in Earth's atmosphere, it's actually visible from space. And ozone is a byproduct of photochemistry of oxygen in an atmosphere. You get enough ozone to detect like this if you have a lot of oxygen in the background atmosphere. And so this is an example of oxygen in an indirect way, but not too indirect, being a biosignature gas, right? So if you look at these three atmospheres spectroscopically, Earth looks different. It looks different in the sense that one has this oxygen chemistry that's going on, and that oxygen chemistry would not be there on Earth if not for biology. So there's a lot of interest then in oxygen as a biosignature gas. Okay, that's great. So what do we know about oxygen on Earth, especially through time? Because Earth is 4.5 billion years old, and when we look at other planets orbiting other stars, we are not necessarily going to see them as in their evolutionary state like Earth is today. We may see them at any point in their history, and their history may look kind of like Earth's history. So let's understand how oxygen changes in atmosphere through the time. And so there's been a large number of geoscientists over a large number of years investigating, not just for this reason, but for many reasons, the history of oxygen in Earth's atmosphere. And this cartoon here from a paper a few years ago is a nice synthesis of what has been found. And the main thing to draw your attention to, so on the first one, on the y-axis here is oxygen, x-axis is time. So here's today on the right, here's 4 billion years ago on the left. And there's a lot of detail here, but the main thing to take away, well, first thing to take away is that this is pretty crude, right? It's like a cartoon. And that's reflecting the degree of ignorance that we have, right? We don't have a lot of detailed information about oxygen. We have to reconstruct it indirectly from the ancient geological record, and the ancient geological record is pretty poor. As many of you know, certainly if you are pre-Cambrian geologists, you know that the further back in time you go, the less you have to work with in terms of geological material. Second thing to take away is that there was a big change about halfway through Earth history. For the first half of Earth history, oxygen was very low in the environment. And then there was a big change to some fraction of the modern amount. This is a log. We have a log scale here on the y-axis. So this change is a little bit exaggerated compared to what it would be on a linear scale. But this is the way we tend to think about it. So we went from a world that had very little oxygen to a world that had some decent fraction of the modern amount of oxygen, and it never went back. We argue a lot about just how much oxygen was at this time, but we never went back to the Archean situation as far as we can tell. And then about at the end of the Precambrian era, we had another rise of oxygen to levels that are kind of like modern. And then after that, we start to get more resolution because we have a lot more rock record to work with. So this halfway through Earth history is this great oxidation event, is what we call it. This one-time transition of the Earth's environment from being largely anoxic to being having strong fingerprints of oxygen in the environment. And this is one of the greatest transformations in Earth history. We wouldn't be here if that transformation hadn't happened. Now, from a astrobiological perspective, it's interesting to ask, well, during what periods of time would Earth have been detectable to astronomers on other worlds aiming telescopes at us to try to see if there's a biosphere using oxygen as a biosignature? Well, today, and for the last 500 million years or so, it would have been detectable with the right kind of telescope. During the middle part of Earth history, during the Proterozoic, you know, debatable, but depends how big your telescope is, it would have been barely detectable with the kind of technology that we're imagining putting in the next generation of space telescopes. But for the first half of Earth history, life would have been undetectable on the planet, even though there's plenty of evidence that there was microbial life on Earth going back to at least 3.5 billion years ago, and arguably earlier. So for the first half of Earth history, we think Earth was inhabited for most of that time, but that biosphere would not have been detectable by looking at oxygen as a biosignature. And even after that, it would have been difficult to detect. So this interplay between detectability and life and oxygen leads to a lot of interest in trying to really reconstruct, well, what was the history of oxygen and what controlled it? Why did it vary the way it did? Right? I mean, ask some first order questions. Is it inevitable that if a planet has life that makes oxygen, is it inevitable that you're going to end up with a 20% oxygen atmosphere? Or are there conditions on Earth that make it particularly unique that allowed that to happen? So these are the kind of questions that one starts asking when one starts looking at Earth history. And this is a very practical question from we like to have a predictive theory. We like to be able to predict, and this becomes a very practical question because we are about to we're about to launch this telescope here, the James Webb Space Telescope. This launches next month, finally. The Hubble Space Telescope exists now. James Webb will exist shortly. The next generation of space telescopes, which are being planned and imagined, are substantially larger and more complex and expensive, and are designed specifically, or will be designed specifically to look for biosignature gases in the atmospheres of planets orbiting other stars. And they're going to be expensive to build, and observing time on these telescopes is going to be limited and precious. They won't be able to look at everything all the time. They'll have to pick their targets carefully. And so we'd like to know which planets are likely to have oxygen in their atmospheres and which ones are not, right? If you're going to use oxygen as a biosignature gas, you don't want to just randomly aim your telescope at any candidate planet. You'd like to have some idea if a given planet is likely to be in this scenario, or in this scenario, or in this scenario, right? You'd like to have some predictive theory that allows you to understand from the age of a planet, from its chemical composition as inferred from its star, and from theory of how planets evolve. You'd like to have some ability to predict. Now, of course, evolution and biology has a lot of randomness to it, but could you at least predict, could we at least get to the point of being able to say, hey, look, if there's life on this planet that is photosynthetic, is it likely to accumulate oxygen or not? So our understanding isn't good enough for that, and we'll walk through that challenge and some of the cutting edge science there now in the next few minutes. So to try to understand what shapes oxygen in the planetary atmosphere, we want at least some kind of theoretical framework to guide our research, even into just Earth history. So we have a very simple way of thinking about this. The rate of change of oxygen in the atmosphere is going to be controlled by the balance between production by sources and destruction by sinks, right? You have things that are making oxygen and putting it in the atmosphere. You have things that are consuming oxygen and taking it out. And since we're talking about geological timescales, we're interested in the long-term geological sources and the long-term geological sinks. So let's first of all talk briefly about sources. So what's the source of oxygen? Well, ultimately, there are some non-biological sources, but we're going to leave those aside. They are important in certain contexts, but that's a different talk. But for the moment, let's focus on the biological sources. The biological source is photosynthesis. It's CO2 and water going to oxygen and organic carbon. And so we have some questions that we might want to ask right away when we look at that curve of oxygen through time and understand that oxygen is produced biologically. We might ask ourselves, did biological oxygen production significantly predate the Great Oxidation event? Right? The biology textbooks say that the reason that oxygen rose 2.5 billion years ago is because that's when life invented photosynthesis that makes oxygen, oxygenic photosynthesis. Many biology textbooks literally say that. But is that really true? Or did biology start making oxygen before then, and the accumulated of oxygen was kept down, kept prevented by other factors? If oxygen production started before the Great Oxidation event, then what kept oxygen from rising earlier? And once we understand that, what are the implications for astrobiology, for the search for life elsewhere? So we're going to walk through these questions and some of the science around these questions. So did biological oxygen production significantly predate the Great Oxidation event? Well, you know, if you're my age, Mariano's age, you probably grew up learning that, yeah, it probably did. Because that was the classic idea that Preston Cloud and others advanced based on things like stromatolites. So stromatolites are fossil preserved microbial mats. And we can argue really about whether or not they were photosynthetic mats to some extent. But there's pretty good evidence if you look closely at the morphology of these things that they were probably photosynthetic, that there were photosynthetic microbes living in these microbial communities. And there's strong arguments that one can make from this detailed morphology that these were probably oxygen producing, there were probably oxygen producing photosynthesizers in those mats, arguably going back to 3.5 billion years ago. It's contentious, but it's a classic argument that was made and it's been refined and it still stands. Banded iron formations are another classic piece of evidence that are used to argue for oxygen in the ancient environment. The presence of banded iron formations, which were deposited mostly in the Archean and Proterozoic, tells you that the oceans were largely devoid of oxygen. Otherwise, you couldn't have had so much iron in the water. But the fact that these precipitated as primary iron oxides, which is what most of us think, means there must have been some oxidation going on in the surface ocean. And so the classic idea is that the surface oceans were at least mildly oxygenated, probably by photosynthetic bacteria producing oxygen to make these banded iron formations. And this is all stuff that one finds before the great oxidation event. What my group has done, and my collaborators, has been to develop other lines of geochemical evidence focusing on the element molybdenum in particular. Molybdenum is an element whose geochemistry in the environment is very sensitive to the amount of oxygen in the environment in a few ways. And one of the key ways is this. So molybdenum in the continental crust is present in igneous rocks primarily or heavily in sulfide minerals, molybdenite as a constituent of pyrite and other sulfides. And when oxygen is present, as those geochemists in the audience know, when oxygen is around, sulfide minerals oxidize and fall apart pretty readily. They weather pretty readily under an oxidative regime. And when that happens, those minerals release their molybdenum into the rivers, which then goes into the oceans, accumulates in the oceans. So today, for example, molybdenum is the most abundant transition metal in the oceans. It's only 100 nanomolars, but that's enough to be very abundant for a transition metal in the modern oceans. So the modern oxygenated oceans have a lot of molybdenum because it accumulates under oxidizing conditions. And then it can get sampled by sediments, and particularly sediments in what are today rare sulfide-bearing environments, like the Black Sea, will sample the molybdenum from seawater. So one can look at ancient sediments deposited under hydrogen sulfide-bearing conditions. So black shales is where we go. One can look at ancient black shales and measure the molybdenum content and also the molybdenum isotope abundances in these ancient black shales. And from the molybdenum content of the black shales, we can infer something about the molybdenum content of the oceans. And the molybdenum content of the oceans is sensitive to the amount of oxygen in the environment, in the atmosphere and oceans. And so there's this chain of logic, right? Molybdenum in the rocks is a proxy for molybdenum in these rocks in particular is a proxy for molybdenum for oxygen in the atmosphere. This kind of application was really pioneered by folks like Tim Lyons and Clint Scott, who we collaborate with extensively. They wrote this lovely paper in 2008 in Nature that tracks molybdenum in black shales through time. We have a lot more data now, but this is a classic paper, so I like showing this data set. So this is showing you molybdenum in black shales through time. So you see here, it kind of looks a little bit like the oxygen curve that I showed you before. In the last 500 million years or so, we see some very large enrichments of molybdenum, which makes sense because in the last 500 million years or so, there's been a lot of oxygen in the environment, which weathers sulfides, which leads to molybdenum being accumulated in seawater, which then can get sampled by black shales. So we can have these events, or these episodes, these periods of time where we have very high enrichments of molybdenum in black shales. Then you go into the Proterozoic, and the record gets worse, but we see modest enrichments. But then we go into the Archean. For the most part, molybdenum is fairly scarce in these rocks, only a little bit above detrital levels. So this is an architecture that was built up during the 2000s. And some of the research that we did was to ask ourselves, well, let's look really intensively. Let's pick one period of time before the great oxidation event and look really carefully at high time resolution to see, can we pick up any evidence of there being oxygen in the environment transiently, maybe during a period of time before the great oxidation event. And that led to this paper here, and then a number of papers that followed. This is a paper in 2007 in Science. What we did here is we looked in black shales at 2.5 billion years ago in the Mount McRae shale, and we found this in molybdenum enrichment here that went up to about 40 parts per million, which is actually a pretty respectable amount above the previous background, and then it fell back down. And we did a lot of associated research around this. It's not just molybdenum concentrations that convinced us that this is a primary signature of the rock that reflected a transient change in the molybdenum content of the water. And we refer to this then as evidence of a whiff of oxygen before the great oxidation event. That, the ambient condition before the great oxidation event was low oxygen, but there were periods of time, there were episodes, we assert, when oxygen was transiently available in the environment and left its fingerprint in transient ways in the geological record. So we interpret this as evidence of trace oxygen in the environment in transient ways before the great oxidation events. Since that time, many workers have looked at many other proxies. So here's the same suite of rocks. Here's 2.5 billion years ago. This is the Mount McRae Shale. Here's the lower black shales. Here's molybdenum. EF stands for enrichment factors. This is enrichment relative to detrital material, to average crust. So we've looked at rhenium. People have looked at the iron speciation, the detailed chemistry of iron in these sediments, nitrogen isotopes, uranium, selenium, molybdenum isotopes, thallium isotopes that you see here. And there's no time to walk through all of this, but what all these proxies point to is that there was a change in the environment that was probably somewhat transient, although left some permanent marks, around 2.5 billion years ago. So a couple 100 million years or more before the great oxidation event. There was transient change in rate intensity of oxidative weathering, in marine oxidation locally, in the larger scale marine oxidation, and also the presence of euxinia, which in non-intuitive ways depends on there being some oxygen around. So we wrote a nice review paper. My student, former student working with me, Chad Ostrander, is now a postdoc at Woods Hole, and another student, Alicia Johnson, who's now a postdoc at University of Chicago. And I wrote this review paper, I think it's very nice anyway, that was published last year, that kind of walks through much of this geochemical evidence, this proxy evidence for whiffs of oxygen. And we think actually there were multiple whiffs. We think there's evidence that there were multiple transient events going back in time. Just for the geochemists in the audience, I won't go over this slide very carefully, but I refer you to this work here by Chad that was published in Nature Geosciences. This is looking at thallium and molybdenum isotopes and focusing on this coupled, this anti-correlation in these rocks. When the isotopes of molybdenum shift light, when the isotopes of thallium shift to lighter values, the molybdenum values shift to heavier, and vice versa. And Chad argued that it's very hard to explain that anti-correlation in any other way than absorption of molybdenum and thallium onto manganese oxides, which would not have, which we argue are the manganese oxides are exist because of oxygen in the environment at this time, as a consequence of a whiff. So Chad argued that there were periods of time, there were episodes when the water column was actually in fact fully oxygenated in shallow waters, and that we see evidence of that in the isotopes. Another set of papers for the geochemists, if you're have a bit more of an experimental and a modeling bent, Alicia Johnson, this other student that I mentioned, who's now a postdoc at the University of Chicago, has a pair of nice papers from the last couple of years. First, doing experimental work, looking at the sensitivity of molybdenite and pyrite weathering to oxygen at really low levels. Nobody had done experiments at levels of oxygen that are representative of what the ancient environment might have been like. So nobody really knew for sure what the kinetics were of sulfide oxidation at those low O2 levels. So Alicia did these experiments in collaboration with Don Canfield and others. And then based on those data, developed a model of how much oxygen you would need in the atmosphere to actually explain the molybdenum data we see in the ancient geological record. And what she found, the upshot is that you don't need very much oxygen you don't need much of a whiff of oxygen to create the signatures that we see in the geologic record. It's fully compatible with the various proxy evidence that we see. So a little whiff of oxygen can lead to a fingerprint of molybdenum that we measure. And so we have then this vision then of that oxygen in the Archean looked something like this. During the first half of Earth history, oxygen was generally low. The oceans were broadly anoxic and hence iron rich, which is to say ferruginous. So the general oceans were loaded with iron too, because for the most part, the oceans were devoid of oxygen. But in the surface environments near shore, there were cyanobacteria making oxygen. So you have near shore surface waters that were oxygenated, is what we would argue, at least at certain periods of time. And beneath those oxygenated waters, one had oxygen minimum zones where organic carbon was settling down and being consumed by aerobic respiration. But because you have low oxygen conditions, that aerobic respiration would then shift into being sulfate reduction. So one would have sulfide production. So what today are oxygen minimum zones in the oceans, during that time would have been sulfide maximum zones, which would be euxinic, which is to say full of hydrogen sulfide. So we think that nearshore environments were often like this in the Archean: oxygen at the surface, anoxic and iron rich at depth, and then with sulfidic wedges in the very productive nearshore environments. again, to folks like me and Mariano and others of our generation, this actually looks a lot like what we were taught when we were undergraduates that the Archean world looked like. But there's been a generation that for a while thought that there was maybe no oxygen at all, but now we're sort of returning and saying, well, there was probably some, a little bit. So to go back to our big question, so what this means is we're asserting that oxygen was being produced by biology during that first half of Earth history, but something was keeping the oxygen from rising in the atmosphere. And just one other line of evidence then, so a very recent paper, this came out just 2 months ago in September. This is now a totally different way of looking at things. This is doing phylogenetic analysis. To me, this is magic. If there's some molecular biologists in the audience, maybe you can explain it to me, but this is beautiful work, at least I'm told it's beautiful, I barely understand it, by Greg Fournier and others, trying to reconstruct through the genomic record what the evolutionary history is of cyanobacteria and oxygen-producing cyanobacteria. And what they argue, from independent of any geochemistry, just from their reconstruction of the phylogenetic record, they argue that oxygenic cyanobacteria that produce oxygen, go back to perhaps as far as 3.5 billion years, which is consistent with what we're starting to see in the geochemistry, right? So the environment was generally anoxic, but the potential to become oxic was there long before the great oxidation event, long before the environment transitioned into an oxic environment that could start to be detected from space. So what kept oxygen down? That's kind of important. If we want to build some predictive capacity, if we want to be able to say, oh, that planet orbiting that star there is likely to have oxygen if it has oxygenic bacteria on it, oxygen-producing bacteria on it, then we need to understand, well, what controls oxygen in an atmosphere? So what kept oxygen from rising? So that's what the question we're going to pursue here. Very quickly, I realize we're low on time. I want to skim the surface of the argument, at least, so you see where we go when we start thinking about this. So if we want to understand what kept oxygen down, even though we think from geochemical and genomic arguments it was being produced, then we need to focus on the sinks. So what's consuming oxygen on long geological timescales? Well, on long geological timescales, what really matters are these downward arrows here. It's reaction of oxygen with igneous rocks during continental weathering. It's reaction of oxygen with volcanic gases coming from submarine volcanoes and subaerial volcanoes. It's reaction of oxygen with metamorphic gases, and it's also submarine weathering, so weathering of igneous rocks on the seafloor. So one can take that very simple equation we had before and make it a little more complicated with a bunch of additional parameters. So this here is the net biological production. This here, we haven't talked about this, but there's also a net production of oxygen when hydrogen escapes the top of the atmosphere. This is a physical phenomenon that we know goes on. So that term has to be here too. And then we have these sink terms of reaction of oxygen with volcanic gases, with metamorphic gases, and with igneous rocks during weathering. So we can take this and ask ourselves, well, so sorry, let me go back here for a second. So this cartoon here, what's kind of sobering if you're a geoscientist or a biogeoscientist interested in thinking about the whole planet, is that this cartoon here kind of represents the level of sophistication of much of our thinking about this. You know, we've done a lot of research at the surface, but those of us who study the surface know almost nothing about what goes on at depth and how the surface environment really interacts with materials coming up from the Earth's interior. To those of us who are Earth surface scientists, the interior is a big box that gives us fluxes that our colleagues who do solid Earth geosciences tell us might have been the fluxes. And then when we talk to our friends who study the Earth's interior and ask them, well, what would the volcanic gas composition of fluxes have been like 2.5 or 3 billion years ago, we learn that there's a lot that we don't know. There's a lot that they don't know. So it's very interesting. In the last decade or so, there's been a number of papers that have emerged that try to, in various ways, explain the rise of oxygen by invoking changes in the boundary conditions set by the solid Earth, the sink terms that we just went over. So a number of papers that are worth looking at. But all of them are kind of recapitulating a classic argument that Dick Holland, who was actually my undergraduate mentor, Dick was obsessed with this oxygen question the last half of his life, and so he theorized a long time ago in the probably 1960s. He started thinking about this, that what could really have made a difference is if the redox state of the mantle had evolved, then you would have an evolution of the redox state of volcanic gases, and that could explain the great oxidation event. And in one of his later papers in 2002, he did sort of a synthesis and he put forward the argument as best he could that gradual changes in the composition of volatiles, of volcanic gases, could have been responsible for the great oxidation event. And he argues that the change that you need is about, in FO2, in the oxygen fugacity of volcanic gases, is about half a log unit or even less. You don't need a huge change in mantle oxygen fugacity translated into gases in order to flip the atmosphere from anoxic to oxic. Now, a number of folks over the years had tried to pin this down. You know, what is the evolution of mantle redox state? And in general, they'd always found that it was not changing over time, but the resolution was not good enough. The resolution was bigger than half a log unit. And so, I was fortunate to lead a big NSF, U.S. National Science Foundation project that funded this research done by Willie Nicholas at University of Maryland, working with Igor Puchtel. Willie was a graduate student at the time, and he did this lovely work looking at vanadium partitioning in komatiites through time. So komatiites are these distinctive basalt-like rocks, igneous rocks that formed under, we think, higher temperatures that are found more commonly in early Earth history, in the Archean. And vanadium partitioning between olivine and melt during komatiite formation is sensitive to oxygen. So he developed this oxybarometer in komatiites and argued that if you look at the vanadium in komatiites, one sees this trend through time. So here's 3.5 billion years ago. Here's the great oxidation event is somewhere here, and then here's after that. Here's today. Delta FMQ is a way of talking about change in oxygen fugacity. So what he argued is there was a shift of about 1 log unit of FO2 in the mantle oxygen fugacity, and he argued if this was translated into volcanic gases, that shift, that secular trend, could explain the shift in the atmosphere from anoxic to oxic, not because of a change in oxygen production, but because of a change in oxygen sinks. Oxygen sinks being importantly the redox state of volcanic gases. There's another group looking at basalts, looking at vanadium scandium ratios in basalts, that came up with this by Albach and Stanio, came with similar kind of result. So both the basaltic of vanadium scandium and the vanadium work by Willie both show this trend of mantle redox evolution of a magnitude sufficient to make a difference to the oxidation state of the surface. So one can then, I'll just whip through this very quickly, one can do a little bit of algebra and make a few assumptions and build a model that then becomes a little more sophisticated to try to actually quantify how this change in mantle oxygen fugacity would have translated into change in atmosphere. So this is work as part of this big NSF project that Shintaro Kodoya, postdoc at the time, did with David Catling, University of Washington, modeling essentially this change in this oxygen parameter with time. This is a parameter that if it's bigger than 1, if you're bigger than 1, it means your atmosphere is likely to become oxic. You're in a net oxidizing situation. And if it's less than 1, you're in a net anoxic situation. And what modeling showed is that this trend in mantle oxygen fugacity sends you on a trajectory in this model such that around 2.5 billion years ago, your probability of being anoxic, if you factor in all the uncertainties, is less than 5%. You cross the 95% confidence threshold that the atmosphere should have been oxic by the time of the great oxidation event. And so we argue in this paper here that I was along for the ride. This is really Shintaro and David Catling's argument that the change in mantle oxygen fugacity was sufficient to flip the atmosphere from anoxic to oxic, starting sometime before the great oxidation event and flipping over, kind of with great confidence to sort of towards 100%, 95+% confidence after the great oxidation event. Kind of fits with what we see in the record. So what this tells us is, understanding how the surface and the interior interact is critical to understanding what goes on with oxygen in the history of Earth. And so now we can ask, okay, if if change in the Earth's interior may be what kept oxygen from rising. So let's go back to our big question. What are the implications for astrobiology? Well, let's ask ourselves this question. Let's imagine two worlds. We got Earth on the left, and on the right, we have a world that is kind of like Earth, but a little bit different. Maybe it's a little bit more massive, maybe it's slightly different chemical composition, or so on. So how does that affect things? Let's say the mass is 10% bigger. How does that affect the evolution of the planet's interior? How does it affect plate tectonics and the interaction of interior gases with the surface? The answer is we don't know. What if there's a different redox budget? What if the iron to carbon ratio in that solar system is a little different, or the carbon to oxygen ratio is a little different than on Earth? What does that do to the redox evolution of the solid planet, and how does that impact the redox evolution of the atmosphere? We don't know. We don't have a guiding theory. What if the tectonics are different? Because let's say the magnesium to silicon ratio in that solar system is 10% different from ours, which leads to a different viscosity of the mantle. So different type of style of plate tectonics. What does that do? We don't know. And how about a different volatile budget altogether? What if the volatile inventory is bigger or smaller? How does that affect the ability of the surface to become oxidizing? We don't know. And so what I assert is that we don't understand this well enough for the Earth to build the generalizable theories that we need to be able to predict what planets that are even just a little bit different from Earth might look like, even if we stipulate that they have life that's making oxygen. So we know that in the Archean Earth, we had life that was making oxygen. We're pretty confident of that. But we know that oxygen didn't take off in the atmosphere for many hundreds of millions of years after that evolution. We don't understand why that happened well enough. We're starting to realize that that requires that we think in an integrated way about the whole planet, about the evolution of the planet's interior and how that couples to the surface. We need to develop this kind of integrated theory in order of how Earth evolved, in order to have a predictive theory of Earth evolution that we could then apply to planets that are a little bit different from Earth and make some kind of prediction about how they're likely to evolve. And that's what I want to leave you with, that I think we as biogeochemists, that's what I am, if we want to really move forward in understanding the biogeochemical evolution of this planet and be able to predict, have a theory to guide us in understanding the biogeochemical evolution of other worlds, we need to talk to our friends who are not biogeochemists. We need to talk to our friends who are mantle dynamicists and solid Earth petrologists and so on and so forth, and work with them to develop an integrated way of thinking about the planet as a whole, and how the surface evolves once life is there. So with that, I'll stop and be happy to take any questions.
Okay,
hopefully I'm more or less on time.
Thank you, Ariel. Brilliant presentation, very stimulating, very fascinating topics, I would say. I mean, so many things that we do not know. So this is, I mean, for the youngster at least, it's very stimulating. So
this is why we do science. And we in schools, you go through school and you think science is all the stuff we know, and then you become a scientist and you realize, oh no, what's actually fun about it is how much we don't know. That's the cool part.
Okay, so we have time for question, and I see that there is Donato Giovannelli. He has a question, so please, Donato.
Hi, Ariel. Donato here from the University of Naples. Thank you very much for the fantastic talk. I was wondering if you.
I was just going to say, I think you've seen this talk, a version of this talk before. I think we've spoken before about it.
Yeah, but there are some. Yes, it was AGU, I think, not long ago. Yes. But yes, there are some interesting points you made today, and I wanted to ask you to comment a little more on the role of mantle fugacity switch. Because what would have changed fugacity to be more oxidized? Would have been, for example, carbonate being subducted? Do we need subduction to change oxygen fugacity in the mantle? Or my understanding was the reduced carbon fixed by biology will actually make it potentially more reductive. So I was just wondering if you can comment a little more, because I'm fascinated.
Sure. Yeah, well, I didn't comment at all. In the interest of time, I didn't even go into at all what might have driven that change of mantle oxygen fugacity. So you're right that to do it by subduction is a little hard, because you don't really subduct oxidized stuff, actually, and it's a little paradoxical. You don't subduct a lot of oxidized material until you start oxidizing the surface. And if you're going to oxidize the surface because of a change of mantle oxygen fugacity, you're at a little chicken and egg problem. So my friend David Catling, who's a big fan of this idea of hydrogen escaping to space, being a driver of these things, David argues that look, if you look at all the terrestrial planets, they all have oxidizing surfaces. They don't all have O2, but they all have oxidizing surfaces. And he says that's because they lose hydrogen to the atmosphere, to space. And so that there's going to be this general tendency of what gets subducted to become more oxidized with time. So David has made that argument. I don't think anybody has shown that quantitatively that works. And there is this other problem, as you mentioned, that once life gets going, you're also subducting reduced stuff, right? So organic carbon. So the idea that I think is more interesting, and I've seen a couple of folks try to advance this now quantitatively, is that there are heterogeneities inside the mantle, redox heterogeneities that evolve with time. So, for example, one could imagine primordial heterogeneities where you have an ambient mantle that is more reducing than certain regions of the mantle that are more oxidizing, and that as that mixes, as that those more oxidized zones kind of mix in with the bulk mantle over time, the bulk mantle slowly becomes more oxidizing. So that's one idea. There's other ideas that I've seen. I can't talk too much about because it's in a paper that I'm reviewing, but arguing that during the magma ocean phase, you could have made a layer at the core mantle boundary of that was more oxidizing due to iron disproportionation into the core, creating a more oxidized layer. So FeO disproportionates, and then as that mixes up into the mantle, you make the volatile source for volcanoes more oxidizing. So there are these ideas, right? Nothing's proven, but those are the kind of ideas that I've seen people start to play with. It's been a big effort to start convincing parts of the community that this mantle FO2 data is being interpreted correctly. This is vanadium komatiite data. So it's only the last couple of years that we finally have gotten those papers out and people say, yes, okay, we're starting to believe that your interpretation is sensible.
Well, fascinating. Yet another way of coevolution between life and planet. Thank you very much.
Yep. Yeah, I mean, think about it. I mean, it's fascinating to think that the evolution of oxygen in the Earth's surface environment might depend on chemistry that happened at the core mantle boundary during the magma ocean phase of the Earth's formation, right? And if that chemistry had been different, we wouldn't have an aerobic biosphere. I mean, that's like mind-blowing, right?
Yeah. Okay, we have another question. I see Alfonso Mota. So please, Alfonso.
Hi, thank you, Professor, and thank you for the great talk. My question was focused on the astrobiology side. So you focused on this talk on the oxygen as a biosignature, but since there's also an oxygenic photosynthesis, and we're not sure if every planet that could have life would have oxygenic photosynthesis, what other biosignatures do you think could be interesting to focus on in the search for life as we know it outside of Earth?
Yeah, so there's a lot of people in the last 10 years who've been thinking about things other than oxygen, partly motivated by partly motivated by what you bring up, which is very good, and partly motivated, science. I'll just say science has fashions, right? So we've been talking about oxygen for a long time. So young people come along and want to think about something new, right? And good, that's good. That's what drives science forward. So let me just say at the outset, I still think that of all the biosignature gases that I see people talk about, if you're going to pick one, if you have to pick one, right, oxygen I think is still the most powerful one to be focusing on. So we can talk about that later. What we really want, I think, is multiple gases. So that's another just philosophical statement. We want multiple lines of evidence. As far as anoxic biospheres, right? So that's a big question, big challenge. So what people talk about a lot is methane, right? So anaerobic biospheres can make methane. The challenge there, of course, is that non-biological planets can make methane quite nicely too. And differentiating that is complicated, it's difficult. So there's a lot of interest in doing isotopic compositions of methane as a way to try to get a better handle on biological versus non-biological sources. That's of course more difficult for planets orbiting other stars. Then there are other gases people look at. This whole business about phosphine on Venus got people very excited because it's hard to make phosphine non-biologically in the conditions of the Venus atmosphere, we think. And we do know that there are microbes that make phosphine, and so, and it's an unusual gas, and so that kind of thing has gotten attention. There are reasons I think that that's a false lead for a situation like Venus, but there is a lot of interest in gases that are kind of unusual to find non-biologically that we know the biology makes. I think all of them are challenging to build a case around.
Okay, thank you very much.
Sure.
We have still time for more questions, but please don't be shy.
Yeah, I'll just say I think the real frontier with biosignatures is to think about coupled signatures of multiple gases. And what might you detect? What might you look for? Any single one is going to have problems, but if you have 2 or 3 different gases that even if none of them is, even though a single one is super high confidence, you can build up a strong case, I think.
Okay, any more questions from the audience?
Mariano, sorry, are you monitoring also YouTube? Because sometimes we have questions on YouTube.
Yeah, I've just had a look. There is no question. At least I don't see any question in the chat of YouTube.
Okay, thank you. I was just mentioning it because last time they were there.
Oh, we have run a little long, probably, so.
Well, I have a question. Do you think that, I mean, we are still looking at the, I mean, we are looking at the ancient record of life on Earth, and it's more a matter of finding new proxy for the history of oxygen, the history of coevolution of life and the planet, or do we need to be more smart with the proxy that we have? Do you think that in the future?
I think since I'm in the business of developing proxies, of course, I always want more better proxies. But I don't think that's the limitation. I mean, the limitation is the geologic record is our big limitation, right? It's just that the further back in time you go, the bigger the gaps are in the geologic record, and that's a fundamental problem. So if we can get smarter about teasing information out from fragments of material that are not beautiful sedimentary strata, then that may be a fruitful path.
Could new proxy developed for diamond inclusion help?
Yeah, well, those sorts of things, right, which get more complicated, right? They get more indirect, but what can you do? What can you do with what could you do to peer through metasedimentary rocks, right? And say something about conditions when those were fresh sediments. Are there things we can do that can look through alteration? That's it's hard, right? But if I was young and just getting into the field, I'd probably think about those things. Kind of like when I was young, I thought about these weird metals and isotopes, right? Because people weren't focusing on them so much, and that turned out to work out. So yeah, I try to think about what records might we unlock that right now we don't pay attention to.
Mariano, can you hear me?
Yeah, go ahead.
I'm wondering if there is still time for one question. It's probably a very stupid question, but I would like to Ariel to get back to one of these slides that is shown. It's about our ability to track using telescope chemical information in other planets. There was a very nice slide that is shown where it was comparing how much oxygen would produce across the history of the Earth and what we would be able to track nowadays within planets that are in the conditional situation, like, for example, the anoxic period or times. And
yeah, I can
see if I can.
I think you mean this slide here.
See if I can see, because I'm using the okay.
You probably meant this one here.
Yes. Very good. So what if I correctly understood what you're suggesting, that essentially nowadays with the telescope we are able essentially to observe or to track an information from an equivalent of the Neoproterozoic oxidation event beyond.
I should not now, but with the technology that is now planned or likely to be developed soon, the next generation space telescopes, that will be detectable. Right, not yet, but it's in sight, right?
Okay. Yeah, because that means essentially that nowadays, I mean, I'm assuming that it's very rare to arrive for a series of coincidences to such a level of evolution of the life in a planet. But that still cut off another, probably much more probable situation where you have a lot of microbial type of life, which is not producing enough oxygen. We are missing all of that. Is that what you're suggesting?
Yeah, well, I'm suggesting that even when life was producing enough oxygen, the planet was consuming it too fast to accumulate, right? And that we need to be thinking about that, right? We need to be, I mean, if Earth is typical, and we don't know that, that's what part of what we're doing. But if Earth is typical, then life gets going pretty fast, and photosynthesis gets going pretty fast, and arguably, and we can argue about it, but I think it's a good case to make that production of oxygen gets going pretty fast.
Yeah.
You know, so why? But the rise of oxygen in the atmosphere seems to take a while. So why is that? And what I'm asserting here is that I think the interactions of the surface environment with the solid planet are critical to that evolution. And so we as astrobiologists and biogeochemists aren't going to be able to really understand why the Earth's surface evolved the way it did just by focusing on the history of life and environment. We need to be thinking about the history and evolution of the solid planet and how those interact. We need to be thinking like whole planet geoscientists, right? Which most people don't do, right? We're very fragmented.
Interesting. Thank you very much for clarifying. Well, that's for me, it's been quite an interesting point, because it's suggesting that probably we are probably missing situation rather than be able to track what is the real population across galaxies or other universe of the evolution of some planets.
Yeah, I think with oxygen, you know, there's a fair amount of attention to what are called false positives. To, you know, could you have non-biological worlds that accumulate a lot of oxygen in the atmosphere? And people, you know, we can model that, and it's possible, but we understand that. There's less attention to false negatives, to worlds that could have lots of biology, and even biology is producing oxygen, but it's not accumulating. And if we can't predict the false negatives, we could end up wasting a lot of time looking for you know, oxygen around certain plants. So let's say it turns out that if the magnesium silicon ratio is different by 10%, the mantle convection is sluggish in a way that prevents that mantle mixing that's needed to bring this oxidized layer from the deep mantle to into the bulk mantle, right? So on a plant, let's say it turns out on a planet with a 10% different magnesium to silicon ratio, even if it has an Earth-like biosphere, it's never going to have oxygen in the atmosphere. In a large amount. Well, so you know that's something we could actually infer the magnesium silicon ratio of a planet from the composition of the star and some ideas of how planets form. So we could predict that if we you know, that's not a good bet, and avoid wasting time on it, right? But we need to get the theoretical understanding to get to that point, right? We're not there. I'm just giving you maybe, right? Ideas.
Thank you very much. Great talk, by the way. Superb.
Thank you.
So thank you, Ariel, for your talk, and thank you everybody for attending the webinar. And I want just to say that we will have more webinars on this series, and the next one on next Thursday will be given by Paul Falkowski, and it will be about the origin of oxidoreductases. So don't miss it. Thank you again, Ariel, and we really hope to welcome you here in Italy as soon as possible. Okay,
that would be great.
We will definitely invite you in
person.
Okay.
Great. Thank you.
Bye bye. Thank you.
Thank you. Bye bye.
Bye bye, everybody.
Bye.